In this video, I will solve the Schrodinger equation H psi equals E psi for the hydrogen atom. The Hamiltonian H is the sum of the kinetic energy operator and the potential energy operator. In the hydrogen atom, there's attraction between the electron and the nucleus right here. The kinetic energy operator is for the electron, therefore you have the mass of the electron here. We neglect the kinetic energy of the nucleus in this Schrodinger equation. Using the atomic units, the mass of electron is 1, the charge of the electron is 1, h bar is 1, and this Coulomb's constant is 1. We have a simplified Schrodinger equation. So it's right here. And then we can express this part, the Laplace operator, in the spherical coordinates. So we convert x, y, z to r, theta, phi. The conversion is straightforward. It's right here. And then we can convert r, theta, phi back to x, y, z right here. And after careful conversion, we have this Laplace operator in terms of r, theta, and phi. And therefore, the Schrodinger equation of the hydrogen atom in atomic units is this. We have this in the square bracket as the Laplace operator. Negative 1/2 times this is the kinetic energy operator. Negative 1 over r is the attraction between the electron and the nucleus. Again, the kinetic energy of the nucleus is much smaller than the kinetic energy of the electron, and thus is neglected here. It's very easy to verify the following functions as the radial function part of the eigenfunction of the Hamiltonian. So if we look at this, there's r, there's theta, and there's phi. So the solution of this Schrodinger equation can be expressed as a product of a radial function of r and an angular function of theta and phi. So the radial function of r can be this. For the 1s orbital, it's e to the power of negative r. For the 2s orbital, it's 2 minus r times e to the power of negative r over 2. 2p orbital, r times e to the power of negative r over 2. And then we have 3s, 3p, 3d. If you pay attention here, there's a rule here. For the 1s orbital, the exponential function is e to the power of negative r divided by 1. 2s, 2p, negative r divided by 2. 3s, 3p, 3d, negative r divided by 3. So for 3s, 3p, 3d atomic orbitals with a principal quantum number of 3, this exponential function decays slower. And over here, for the 2p orbitals, the exponential function decays faster than the 3s, 3p, 3d. And this 1s orbital decays the fastest, e to the power of negative r. And also, we can clearly see where the nodal surfaces are. For the 2s orbital, when r equals 2, there's a nodal surface, and it's spherical. Over here, we see a r, but later we'll see this r will be combined with the angular functions, and you will see the nodal surfaces will be the x, y, or z planes later. Same here for the 3s orbital. We can clearly see that in this quadratic function, there are 2 possible roots for r, and therefore there are 2 nodal surfaces in the 3s orbital. And also there are 2 nodal surfaces in the 3p orbitals. One is r equals 6. The other one is the x, y, or z plane. And over here, the only thing we can tell is there will be 2 nodal surfaces, but this r squared will have to be combined with some functions of theta and phi, and I'll talk about those nodal surfaces later. So again, those are the radial functions. The 1s function decays faster, the 2s, 2p slower, 3s, 3p, 3d the slowest. When SI units are used, the above radial functions are actually this. They look much more complicated. You see this A naught? A naught is 1 atomic unit of length. So over here, this is e to the power of negative r divided by A naught. A naught again is 1 atomic length, 1 atomic unit of length, which is equal to 0.529 angstroms. So this is why we prefer to use the atomic units instead of the SI units. Again, if you use SI units, you see this radial function becomes really complicated. Now let's look at the angular functions. So first, let's look at this function. This is the angular function of two variables, theta and phi. L and m sub L are quantum numbers. L is the three-dimensional quantum number of the angular momentum of the electron. And m sub L is the z component of that three-dimensional angular momentum. So when L equals 0, m sub L can only be 0. And this angular function is a constant. That means this is spherical. It does not depend on theta or phi. When L equals 1, m sub L can be 0, -1, or +1. So over here, when m sub L equals 0, you have this cosine theta. And cosine theta is simply z over r. Later, you will see this angular function is related to the pz orbital. And when L equals 1, m sub L can be ±1. The function is sine theta times e to the power of plus minus I phi. And this is a linear combination of cosine phi and sine phi. If you have sine theta times cosine phi, that's actually x over r. If you have sine theta times sine phi divided by, if you have sine theta times sine phi, you get y over r. So really, this is a linear combination of x and y divided by r. Now, when L equals 2, m sub L can be 0, ±1, or ±2. When m sub L equals 0, you can see this function is simply 3z squared minus r squared over r squared. This corresponds to the dz squared orbital. And when m sub L equals ±1, you have sine theta times cosine theta times, over here, a linear combination of cosine phi and sine phi. So really, this part will give you the linear combination of xz and yz over r. So where's the z? This cosine theta is z over r, and sine theta times cosine phi is x over r. Sine theta times sine phi is y over r. So this part is actually a linear combination of xz and yz over r squared. Finally, when L equals 2, m sub L can also be ±2. And we have this cosine sine theta squared times cosine 2 phi plus minus sine 2 phi. And this part is a linear combination of, again, cosine 2 phi and sine 2 phi. So if you have cosine 2 phi is simply x squared minus y squared over r squared. And sine 2 phi is simply 2 times xy over r squared. So really, this part will give you actually two other d orbitals. These two functions are associated with dxy and dx squared minus y squared. Again, dxy is proportional to x and y, of course, and x is proportional to sine theta cosine phi, y is proportional to sine theta sine phi. And then this angular functions look like this. This is the first one when L equals 0, m sub L equals 0. Over here, when L equals 1, we have actually 3 p-type orbitals. And then this is when L equals 2, when L equals 3. So now we need to combine the radial function of R and the angular function of theta and phi. We will be able to construct the wave functions of all the atomic orbitals in the hydrogen atom. And then when the principal quantum number n equals 1, we have actually 1s orbital. And I'm writing out the unnormalized wave functions for simplicity and convenience. It's just exponential function e to the power -r. And when this principal quantum number n equals 2, we have e to the power of negative r over 2, and we can see there's a nodal surface. When r equals 2, this wave function becomes 0. Therefore, there's one nodal surface in this 2s orbital. How about the other atomic orbitals? So we have all other atomic orbitals right here. I'm going to use a larger font size to make it more clear. So again, L can be from 0 to n minus 1. So when n equals 2, L can be 0, L can be 1. When L equals 0, you have the 2s orbital with a spherical nodal surface here at r equals 2, multiplied by this exponential function, which decays slower than the 1s orbital. So how about when L equals 1? When L equals 1, m sub L can be 0 or negative 1 or positive 1. When m sub L equals 0, you have 2pz. You combine the radial function and the angular function for 2pz. You get z times this exponential function. How about 2p plus 1, 2p minus 1? They are actually complex functions. They are actually linear combinations of 2px and 2py. So if you combine this 2p plus 1 and 2p minus 1, you get either 2x times the exponential function if you do addition, or you get 2i times y times the exponential function here if you do a subtraction. So really 2px and 2py are the two linear combinations of 2p plus minus 1. So why do we have this different kind of expressions? So this 2p plus minus 1 functions are good in that they tell us the z component of the angular momentum of the electrons. However, these two functions are complex functions. This 2px and 2py are not eigenfunctions of the three-dimensional angular momentum operator or z component operator. So they don't tell us anything about the angular momentum. However, they are real functions, and it's easier to visualize these two functions. And also, it's easy to see that in the 2px orbital, there's a nodal surface when x equals 0. In the 2py orbital, there's a nodal surface when y equals 0. Again, they are simply just x or y multiplied by this exponential function. I'm sorry about this mistake here. When n equals 3, it's a bit more complicated. First, 3s orbital. It's a quadratic function of r times e to the power of negative r over 3. If you look at this part, there are two possible roots of this quadratic equation if we set it to be 0. Therefore, there are two nodal surfaces in this 3s orbital, both spherical. Now let's look at 3px, 3py, 3pz. Again, this 3py and this 3px are linear combinations of 3p plus 1 and 3p minus 1. Again, 3p plus 1 minus 1 tell us the z component of the angular momentum, and this 3px, 3py give us the shape of these two atomic orbitals. And we can clearly see in this 3px there are two nodal surfaces. When x equals 0, this wave function becomes 0. So it's a plane. And then when r equals 6, this wave function is 0. That's a spherical nodal surface. Same here. For 3pz, again, we see a symmetry. That's just 6 minus r times the exponential function e to the power of negative r over 3 times either x or y or z. All right, 3D orbitals. 3D orbitals first, 3D z squared. Well, this wave function is not proportional to z squared. It's actually proportional to 3z squared minus r squared. And then there's an exponential function here. Again, the exponential function is the same for 3s, 3p, and 3d. And then we can find there are two nodal surfaces because z equals r times cosine theta. So this nodal surfaces are simply cosine theta equals plus minus the square root of 1 over 3. All right, there are two nodal surfaces. Therefore, the nodal surfaces look like two cones, one pointing up, one pointing down. And then we have 3D xz and yz. They are simple. They're just xz times this exponential function, and yz is simply just yz times the exponential function. And over here, there are two nodal surfaces when x equals 0 or z equals 0. Over here, also two nodal surfaces. How about 3D xy? Again, two nodal surfaces when x equals 0 or y equals 0. This 3D xy becomes 0. And these two are different. If you look at this carefully, over here, there are also two nodal surfaces. But where are those two nodal surfaces? When x equals y, or when x equals negative y. Over here, it's when x equals 0 or y equals 0. So the locations of the two nodal surfaces are different. And how to get the energy of those atomic orbitals? The equation is very simple. You just need to know the principal quantum number n. And then the atomic orbital energy, E sub n, equals negative 1 over 2 n squared atomic unit. One atomic unit is 4.36 times 10 to the power of negative 18 joule. And we can easily tell that the 1s orbital has negative 1/2 atomic unit energy, or simply you can say 1/2. 2s, 2p orbitals, they have the same energy, negative 1/8. How about 3s, 3p, 3d? Well, they have the same energy, negative 1 over 18. That's it.